VLSos here. This is a video lesson on derivative by definition, the spinal cord of calculus. Let's remind ourselves of a situation in which we can have a function that curves. Let's call it f. And if we have an interval that starts at a and a value f at a and a second location at a plus some change in x, we'll have a second point whose value is found as f at a plus that change in x. We can connect these 2 points with a line, and we could call that line a secant line because it's intersecting the function at 2 points. We could analyze the average rate of change of this function from one point to the next by finding the slope of the secant line. The slope of the secant line is the average rate of change as you go from one point to the other. That's a slope calculation. We abbreviate AROC. Average rate of change is a rise over a run between these two points. We have a rise, which is the difference in these function values. The latter value f at a plus delta x minus the former value f of a. And if we divide by the run, the difference in a and a plus delta x, we'll find the slope. The difference between a and delta x is the change in x. This is for an average rate of change, the slope of a secant line. If we take one of these points and slide it infinitely close to the other, such that the location then becomes the same, and there is no distinction between the 2 points, then the line is no longer a secant line. It grazes the curve at one point. We call that a tangent line. So we no longer have an average rate of change. The slope of this tangent line would be the instantaneous rate of change, the exact amount of change at any single point. It's the slope of the tangent line. The calculation is very similar to the average rate of change. We still need to find the rise over the run, or f of a plus delta x minus f of a, the rise, divided by the run of delta x. But the change in x between these 2 points is getting closer and closer to 0. Or if we take the limit as that delta x goes to 0 of this average rate of change, we could then call it the instantaneous rate of change, IROC. Now, this expression matches this presentation where we're talking about a specific location A and then a second location delta x away. But we can generalize this presentation. First, instead of the difference between these 2 points being delta x, we're going to give it a single letter, often h. And our expression then is going to use any location x instead of a specific location a. So the presentation looks like f at x plus h instead of a plus delta x minus f of x all over h. Same calculation, but we've changed the presentation by generalizing it to the any location in the domain x. And instead of delta x, we're using h. So we take the limit as h goes to 0 to get the instantaneous rate of change of any function at any location. And we call that not IROC, but the derivative. And we have notation for it, if we're using the function and calculating this by the definition of a derivative, then the notation for it, once we find that function, is f prime of x. F is a function, f prime of x is the derivative of that function. For example, let's define a function g is equal to something that we've worked with in the past, x squared. If we're to want to calculate the derivative of that function, which we also call a slope function, it's a function that calculates the slope of the tangent line, the instantaneous rate of change of that function at any value x. By definition, g prime of x will be the limit as h approaches 0 of the g function composed with x plus h. If the g function is x squared, then it's going to be x plus h that we need to square. Continuing with the definition, minus the function, in this case the g function, all over h. Now, if we're going to process this and get a function in simplified form, we can't take the limit immediately because it will cause a division by zero error. So I need to manipulate this algebraically, and so what I'm going to do is I'm going to square this and combine like terms, and then we'll attempt to take the limit. Squaring x plus h is x squared plus 2xh plus h squared. Continuing on, minus x squared all over h, and we're still taking the limit as h goes to 0. I can see that I have two terms that can cancel. And then what I'm going to do with the remaining terms is I'm going to divide by h. 2xh divided by h leaves the 2x. H squared divided by h leaves an h. And we're still taking the limit as h goes to 0. But now I can attempt the limit because I no longer have a division by zero issue. The limit as h goes to 0 of this term that doesn't contain an h remains 2x. And h goes to 0. Simplified, I get 2x, which is a general expression for the derivative of g. 2x is equal to g prime of x, the derivative of g. What does this mean? Let's get a visual. If the g function was parent quadratic, the familiar parent parabolic curve, then the derivative function is the linear function 2x. I could graph it. It's a line that has a slope of 2, passes through the origin. If the parabola is g, the line is g prime, the derivative. What does that mean? It means that the line's values are the rate of change at any g value. In other words, if I want to put 1 in for x, I can find the value at g of g is 1. But the rate of change at 1 is the value of the derivative of g at 1, which is 2. Meaning, if I drew a tangent line to this point, the slope of that tangent line would be 2. Let's do that again. If I put -1 in for x, I could calculate the value of g to be +1. But the rate of change of g at -1 is the value of g prime at -1, which is -2. If I drew a tangent line to the curve of g at -1, the slope of that tangent line would be -2. And this works for every value of x. The relationship between g and g prime is that g prime is always the slope of the tangent line, the instantaneous rate of change of g at that same value x.